Any questions? So I'll begin. So yesterday or last week we discussed free scalar field theory at finite temperature. So today we are going to discuss interacting scalar field theory. In particular, I will consider phi to the 4 interaction. So the action in the Minkowski space will be integral d4 x. So let me write it as ddx dt. I should just point out that in the review that I had referred to, this is taken as lambda over 4. Okay, so many of the explicit factors will be different between what I write and what you find in the review. So now we go from the Minkowski action to the Euclidean action by simply using the fact that if we take t to minus I tau, then ISM, which appears in the exponent of the path integral, this is supposed to go to minus AC, and so this gives the expression for AC as integral ddx d tau Okay, so this part is the same as what we discussed last time, that's the free field action, and all that has changed is the addition of this interaction. And then we can calculate the partition function z as the result of a path integral d phi e to the power minus AC, and you have to use the boundary condition that phi at x tau plus beta is phi of x tau, which is the periodic boundary condition, and beta as usual is 1. So all that differs between 0 temperature and finite temperature field theory is that the integral that you have to perform has to be done over periodic functions. And our goal will be to try to find a systematic way of evaluating this. So let's denote by z free the partition function of a free theory. Function of free field theory, free scalar field theory. This is what we calculated last time. And what we will be focusing on is the calculation of z over z free, okay, because z free is already calculated earlier. Okay, so we will calculate the ratio. But let me first take the expression for z and expand it out. So I will write this as integral d phi e to the power minus AC, I will write as s free E. So this is the free part of the action, okay, which is this part, and then minus and minus Si. This is the interacting part of the action. So let me write Si. Si is basically integral d tau e dx lambda over 4 factorial 5 to the 4, and then I'll just expand it out. So it's integral d phi to the minus s p e, and then sum over n equal to 0 to infinity 1 over n factorial si to the power n. So now if we calculate z over z free, okay, we divide this by integral d phi to the minus ac free.
So minus 1 whole to the power 8.
Minus s, thank you. So now the ratio of z to z free is the ratio of this over a similar path integral with just d phi to the minus si free, ac, the Euclidean free action, and this of course can be evaluated in terms of Feynman diagrams, okay, because we just simply evaluate the correlation functions that appear here. Those are the free field correlation functions, because what appears in the exponent here is as a free action. So z over z free is sum over Feynman diagrams. With no external things. Okay, these are also known as sometimes bubble diagrams. So for example, this is the lowest order contribution. Maybe I should write it down, the Feynman rules. Okay. So let's, before drawing diagrams, let me write Feynman rules. Feynman rules. So the vortex, which is just this 4-point vortex, its associated factor is minus lambda over 4 factorial. Right? This, because SI has lambda over 4 factorial, okay, so that's what appears in this vortex factor. Propagator this is Euclidean propagator, of course. So this will be given by 1 over omega n square plus k vector square plus m square. Okay, this is what we saw for the 2-point function in the free theory. Okay. So the only difference is that this is like the ordinary propagator of a scalar field theory, except that the zero component of the momentum is now quantized. Okay, it's written as omega n, okay, where omega n is 2 pi n by beta. And loop momentum will now be characterized by a discrete integer n, which characterizes the energy component, and a vector L, okay, which is the spatial components of momentum, and loop momentum integral, okay, which you normally write as integral d4L over 2 pi to the 4, that will be given by t times sum over n integral ddk over 2 pi to the t, okay, where d will take to be 3 minus 2 epsilon as before, because we have to regularize all of the integrals. So this basically follows from the fact that when you discretize the zero component of the momentum, this is what appears. So for continuous energy integral that happens at zero temperature, you have gotten a dk0 by 2 pi, right? Okay, where k is Euclidean energy. So this, when you discretize, it becomes 1 over 2 pi, then 2 pi by beta. So why 2 pi by beta? Because 2 pi by beta is the interval in energy between two successive energy values. Okay, so 2 pi by beta times sum over n. So this is 1 over beta sum over n, which is also t sum over n. Okay, that's where this t comes from. Is this clear? Okay, so these are the Feynman rules. Okay, and now with these Feynman rules, we will try to calculate some simple diagrams. Are there questions?
What's the d?
What is that?
3 minus
2 epsilon. This is eventually we want to dimensionally regularize, right? So d is the number of spatial dimensions, okay, which are taken to be 3 minus 2 epsilon because epsilon is a regulator, right, in dimensional regularization. It's 3 because this is only spatial directions, right? The moment the
2 is
pardon?
2 epsilon.
Oh, that's just convention, right? You're going to put minus epsilon also. Okay, we have used 2 epsilon because often you have division by 2, right, which makes it, which is simpler if you have 2 epsilon. Okay, so let's look at this one loop diagram. So first of all, this vortex gives a minus lambda over 4 factorial. Now, two loop integrals, it's clear that they are the same, right? So you can just write the result for one and then square it. So that's d times sum over n integral ddk over 2 pi to the t. Okay, only one propagator, so 1 over omega n square plus k square plus m square. So this whole thing will be squared. Okay, and then you have to put combinatorial factors. So combinatorial factors here are not hard to figure out. So there are 4 lines coming out of this. So you basically have to find the number of ways you can pair them, right? So if there are 4 objects, right, there are only 3 ways of pairing them, right? If you have 1, 2, then the rest, other one is 3, 4, or 1, 3, 2, 4, or 1, 4, 2, 3. Right? These are the 3 different ways of pairing it. So times 3. And finally, there is a momentum conserving delta function. Okay, that we shouldn't forget. So recall that you normally have a 2 pi to the 4, or let me write 2 pi to the 4 delta 4 of 0 in this case. Why 0? Because there is a momentum entering, right? So total momentum entering is 0. So this looks a bit singular, but of course you know what it means. This is delta function of momentum and energy set equal to 0. So 2 pi to the 4 delta 4 of 0 is basically the volume of space-time. Is this clear? Right? You can think of this as integral d4x e to the I k dot x at k equal to 0. Right? This would have given you 2 pi to the 4 times delta 4 of k. At k equal to 0, it's just integral d4x, which is the volume of space-time. So this basically is just V times beta. Okay. So V is the spatial volume, okay, and beta is the volume that comes from the time coordinate, the tau coordinate integral, right? Because tau is periodic, okay, the tau takes value on a something. So V times beta.
So delta D plus 1.
Pardon?
Delta D plus 1.
Yeah, we should write, you can put delta D plus 1, 2 pi to the D plus 1. Okay, but this is still, yes, right? This V will be D dimensional volume. Is this okay? Are there questions?
Here only the bubble diagrams will be there.
Yeah, only the bubble diagrams will be there because
Sound like
we have no external legs, right? When you try to calculate correlation function, then of course there will be other diagrams, right? But there is no external line, right? We are not calculating correlation functions. We are just calculating the partition function. Right? That's the only bubble diagrams are there. Okay, normally in quantum field theory at zero temperature, you don't even worry about these bubble diagrams because they cancel in the numerator and denominator, right? You always divide by the partition function, right? So the partition function is not what is of interest in at zero temperature quantum field theory, right? But here, partition function, well, of course, correlation functions are also of interest, but partition function also is of interest, right? That's why you have to analyze the bubble diagrams. Okay, other questions?
So means precisely k tending to 0, this V tends to infinity.
I mean, this formula is valid in general, right? Infinite volume, right? But as k goes to 0, V will tend to infinity, right? But if you put it in a periodic box, okay? See, if you had put it in a periodic box, then you will not get this, but you will get a Kronecker delta. Okay, so you can make sense of this by putting it in a periodic box, okay? And there you will see that this factor is really the total volume, space time. Okay, if you go back and see in your quantum field theory, where does this such factor like this come in, right? It came in by regularizing the volume by putting it in a finite box and then letting the box size go to infinity. Okay, now at order lambda square, right, there are other diagrams. This, for example, is one diagram, okay, which you have to worry about. There are diagrams like this. That's not. Yeah, this is lambda square. But there are also diagrams like this. Okay, this is also order lambda square. Okay. These diagrams will come with factors of beta times v, okay, because there is a momentum conserving delta function. This one will come with a factor of beta times v whole square, right? Because for every connected component there is a momentum conserving delta function, so you get beta v from here and beta v from here. So what we will show now is that when you sum over all of this, then this becomes the exponential of connected by bubble diagrams.
All of it.
Pardon?
After summing all of it.
After summing all of it, yeah. So sum of all this, right, with 1 plus all of this.
And
Also?
this one, all of the
Yes, this one exactly. So this one also. 1 plus all of this. Okay. Basically, proving this, we have to make sure that the combinatorial factors work. Because it's clear that diagram by diagram we can compare. Right? Suppose you have exponential of a1 plus a2. When you expand it out, you will get terms like a1, a2, a1 square, a2 square, a1, a2. Right? a1 is like a single connected diagram, a2 is like another single connected diagram. a1, a2 is combination of a1 and a2. a1 square is two bubble diagrams, each of which is a1. Right? a2 square is two bubble diagrams, each of which is a2, and so on. Okay. So at the level of diagram, it's clear that there is a one-to-one correspondence between the terms which appear here and the terms which will appear there. Okay. The disconnected diagrams will come when you expand the exponential to higher orders. Okay. When you take the products. Okay. But the non-trivial part is to check that the combinatorial factors work out. Okay, so I'll try to now go through the combinatorial factors in a little more detail and see how it works. So let's suppose we have a diagram with two connected components, a1 and a2. Okay, this a1 is of order lambda to the n1, and this a2 is of order lambda to the n2. Okay, so let me write down also explicitly the form that we will assume. So let's assume that A1, if we just had a single bubble, okay, just A1, so that's of course one of the diagrams. Its contribution is given by minus lambda over 4 factorial to the power n1 times 1 over n1 factorial times I a1. This shows that it's of order n1, there are n1 vortices, right? That's why I have raised minus lambda by 4 factorial to the power n1. 1 over n1 factorial shows that because this is coming from exponential si minus si expansion, right? It should be accompanied by 1 over n1 factorial, right? That's this. And then whatever is left, I am calling IA1. Okay? This contains the rest of the combinatorial factors and everything else. And similarly for A2, let's suppose you have minus lambda over 4 factorial to the power n2, 1 over n2 factorial, IA. Now let's try to see what will be the contribution from this one, A1. This uses n1 plus n2 vortex, right? So it will have a term of the form lambda over 4 factorial to the power n1 plus n2 times 1 over n1 plus n2 factorial. Now we have to look at its combinatorial factors. Now in calculating this combinatorial factor, we will not worry about the combinatorial factors that comes from the exchanging the vortices inside A1 or exchanging the vortices inside A2 or various ways of contracting inside A1 and A2, because those are already included in IA1 and IA2. The relevant part that you have to count is in how many ways this diagram has more possibilities compared to the product that will accomplish. So that comes from the fact that we have altogether n1 plus n2 vortices, right? Out of which we have to use n1 vortex for this and n2 vortex for this. So which of those n1 plus n2 vortices we are going to use for A1, that possibility we have to count, right? Because that wouldn't have been counted individually inside the combinatorial factors of A1 and A2. So that number is n1 plus n2 Cn1. Right? How many ways you can choose n1 vertex out of n1 plus n2 vertex? Once that combinatorial factor is counted, right, then the rest is just IA1 times IA2. Okay, rest of the combinatorial factors are already included in A1 and A2. Is this clear? So this is the extra combinatorial factor that we have to count in this diagram compared to individually inside A1 and individually inside A2. So this is easy to see, evaluate. So this gives you 1 over n1 factorial minus lambda over 4 factorial to the power n1, 1 over n2 factorial minus lambda over 4 factorial for n2. Let me write I n1 here, I n2 here, because this n1 plus n2 choose n1 is just n1 plus n2 factorial divided by n1 factorial times n2 factorial, right? That cancels this. This just becomes 1 over n1 factorial times 1 over n2 factorial. That's what I have written there. And now you can see that this is exactly what would appear in the exponential. If the exponential had a term 1 over n1 factorial minus lambda over 4 factorial to the power n1 times I n1 plus 1 over n2 factorial minus lambda over 4 factorial to the power n2 times I n1 plus these are two of the connected diagrams, connected bubbles. Right? A1 and A2 we had assumed are connected bubbles. So this is, if we expand this exponent, right, one of the terms will come from just a product of this and this. Okay, no 1 over 2 factorial. This is quadratic, but when you square it, you get a 2. Right? So no 1 over 2. So this is exactly the product of this and this that will get. Is this point clear? Is it okay or should I repeat it?
What is this IN1?
IN1, sorry, IA1. IA1 and IA2. Okay, these are these things that happen. Okay, so now let's consider another example. Pardon?
When you calculate this combinatorial factor,
Yes.
for this connected to this 1 over n1 plus n2 factorial, what argument will be?
Oh, 1 over n1 plus n2 factorial came because this is order n1 plus n2 diagram, right? So Si to the power I mean you have to expand to n1 plus n2, right? That comes to the 1 over n1 plus n2 factorial, right? So that's this one. So this came from the expanding the Si, exponential minus Si. This is a combinatorial factor. How many ways you can choose n1 vertex out of n1 plus n2?
So, yes, if we are not divided by Z free, then
Yes.
so then what will be the difference in diagrammatic means
Well, if you don't divide by Z free, then there is no direct diagrammatics, right? Because Z free, I mean, we want to, I mean, how does this work? That we have integral d phi e to the minus s, right? Minus si, right? Which we are expanding. Okay, e to the, you have integral d phi e to the minus s phi, and then sum over minus si to the power n by n factorial, right? And then you are dividing by integral d phi equity minus x. So because of this division, okay, this becomes a sum of correlation functions in the field theory. Right? Because it's SI, you just expand it out. Right? We don't think of this as an interaction term, just a bunch of phi's, right, whose correlation function you have to calculate, and it's a correlation function because of this division. That's why I have divided by z free, right, so that you can interpret this as a correlation function of the phi's that come from SI, and that's what gives the Feynman rules. But this is not a problem because you already know S free. I mean, we already know Z free, right? So eventually, when we have to try to calculate Z, we have to just multiply by Z free that we have already calculated last time. But the Feynman diagram interpretation holds directly only for this ratio. Is this okay? Now, let's suppose I don't want to erase this. Okay, let's say we have this situation. A1, two bubbles identical. Okay. So now let's see what the combinatorial factor. So this is of order 2n1 vortex, right? This has 2n1 vortex. So minus lambda over 4 factorial to the power 2n1, 1 over 2n1 factorial, then you have I a1 square, right? This gives I1, this gives I1. Okay, that's weird. Now the combinatorial factor. So altogether we have 2n1 vortex. Right? We have to choose n1 out of this 2n1. So 2n1 cn1. However, now there is overcounting. There is overcounting because if instead of choosing this particular n1, you would have chosen the complementary set, it would be the same diagram. Right? Suppose you have 4 objects, right? You choose 2 out of 4. Right? If you choose the first 2 and if you choose the last 2, they give the same diagrams. Right? Because exchanging this gives you the same diagram. So you have to divide by half. And you can easily verify, so this becomes again 1 over n1 factorial square, right, combination of these two. And you can easily verify that that's again consistent to the expansion of this. Right. Now the term that you are looking for is the square of this. Right? But in the exponential of the exponential, when you take the square of this, there is a 1 over 2 factorial. Right? That 1 over 2 factorial is this half. Okay, so the combinatorial factors again agree. Is this clear? So now we'll try the general case. So let's suppose that we have a bubble with k1 copies of A1. Then k2 copies of A2. and finally this AM KM copies of AM. Okay, this is a general case, right? If you have disconnected bubbles, then there are certain number of copies of one kind of bubble, certain number of copies of another kind of bubble, certain number of copies of a third kind of bubble, and so on, right? So this is the general case, and we will do the counting. Okay. And again, we will follow the same convention that I minus lambda over 4 factorial to the power n1 times IA1 will be the contribution that we would have gotten just from this bubble. Okay, just one connected bubble diagram. Okay, similarly, minus lambda over 4 factorial to the n2 times IA2 will be the contribution that we would have gotten from this bubble, and so on. So with this notation, let's try to calculate the total contribution from this. So you get minus, okay, so first of all 1 over, so what is the total order? See, each of these is of order A1, N1. Okay. So there are K1, N1 vortices just coming from these, K2, N2 vortices coming from these, similarly Km, Nm vortices coming from this. So 1 over sum over Ki, Ni, I equal to 1 to M factorial, and then minus lambda over 4 factorial to the power sum over I equal to 1 to M Ki Ni. Then we have I A1 to the power M1, I A1 to the power K1 up to I M to the power K. So that's the contribution from individual connected bodies. And now you have to look at the extra combinatorial factor that comes in this diagram, but which wouldn't have been included in the individual bodies. So we have altogether these many vortices, right? Say, let's call this number some, say, capital N. Okay, capital N vortices. We have to choose from capital N vortices. First, N1 vortices that goes in here, right? N1 vortices that go in here, N1 vortices that go in here, and so on. And then N2 vortices that go in here, N2 vortices that go in the next one, and so on. So that number is given by n factorial. So n is basically sum over I Ki Ni, total number of vortices, n factorial divided by n1 factorial to the power m1, n2 factorial to the power k1, k2 to nm factorial to the power km. Is this clear? Okay, out of n we are choosing these many vortices, right? You are dividing, you are basically partitioning n, okay, or dividing n objects into smaller sets. However, as in the last case, there is overcounting. The overcounting comes from the fact that these vortices that you have chosen here, exchanging these with these do not change the diagram, right? Or exchanging these with these do not change the diagram. So you get 1 over m factorial because you have done an overcounting of m factorial, m1 factorial, sorry, k1 factorial. So you get 1 over k1 factorial, 1 over k2 factorial, up to 1 over km factorial. Okay, this is the correct counting. So let me write this expression again in a somewhat neater form. So what we get, this one cancels this. So what we get is minus lambda over 4 factorial to the power n1 times I a1 to the power k1, then minus lambda over 4 factorial to the power n2 I a2 to the power k2 up to minus lambda over 4 factorial to the power nm I m to the power km. Then you have 1 over k1 factorial, k2 factorial up to km factorial. Is this clear? That's what that expression gives. And then now you can check that this is exactly what you get if we take exponential of minus lambda over 4 factorial times IA1 minus lambda over, I think I missed out some things. This should be multiplied by 1 over n1 factorial. Right? These factors are still not doing 1 over n2 factorial, 1 over n1 factorial. So exponential minus lambda over 4 factorial to the power n1, 1 over n1 factorial I n1 plus minus lambda over 4 factorial to the power n2, 1 over n2 factorial I n2, and so on. Okay, if you expand this exponential, the coefficient of IN1 to the IA1 to the power k1, IA2 to the power k2 up to IAM to the power km will be exactly what we have here. These 1 over ki factorials, these come because when you expand these to k1th power, you pick up a 1 over k1 factorial. Right? So when you pick up the cross terms, then that 1 over k factorial cancels out. Right? Just like you saw exponential a1 plus a2 when you expand. Right? The coefficient of a1, a2 term doesn't have a half. Right? Coefficient of a1 square has a half, coefficient of a2 square has a half, but coefficient of a1, a2 is just 1. Right? So this is the correct count. So this shows that the combinatorial factors work out correctly, and indeed z over z free is given by the exponential of the sum of our connected bundles. Okay, are there questions? So log of z over z free is just sum of our connected bundles. So if you want to calculate the free energy per unit volume, free energy per unit volume, this is given by, so free energy per unit volume is minus T over V log Z. Right? So let's call it F. So F minus F free. Okay, free means this is the free energy per unit volume in a free scalar field theory. This is what we already computed last time. So F minus F free is given by minus T over V log Z over Z free. And now we see that there is a simplification, because log of Z over Z free, which is the sum of our connected bubbles. Okay. Each Feynman diagram there has a factor of beta times V. Right? Because you have one connected bubble, so there is only one momentum function having delta function, right? Just a single factor of beta times V. That exactly cancels this T over V. Right? Beta cancels T, beta times T is 1, and V cancels. Okay, V over V is 1. Okay. So this basically simplifies our life. So this cancels beta V factor.
When you plan the finite quantity.
Pardon?
So this is a finite
This is a finite quantity in the V goes to infinity limit. So the only thing you have to keep in mind is this minus sign. Okay, this is something that you have to explicitly include. So after you sum over connected diagrams, you have to multiply by minus 1. Okay, that's the only thing you have to keep in mind. So now let's calculate the order lambda contribution to F minus Fp. Okay, so now we just have to sum of our connected bubbles. There is only one diagram, which is this one. So its contribution, the overall minus sign, because of this minus sign over here, then you have minus lambda over 4 factorial, we had the combinatorial factor, that's 3, and then we wrote down this integral t times sum over n integral ddk by 2 pi to the d 1 over omega n square plus k square plus m square. We have the square of this. But this integral we evaluated last time. Okay, in a different context, we evaluated it because we are trying to calculate the free energy of a free theory. Right? The derivative, of that with respect to the mass had this integral, right? And this integral we had called IMT, I think, right? I is a function of MIT. Okay, so you have already evaluated this, you can just look up your notes and you find the answer for this. So let's write F is F free plus, so it's plus because these two minus ones cancel and this is lambda over 8, right? Lambda over 8 I n t square. Okay, this is our formula for one loop, the free energy to order lambda. The free energy of this scalar field to order lambda. Okay, now, if you remember our discussion last time, we wrote I as a function of two terms, IMT, we wrote as a sum of two terms. One is I0. I0 is the value of I in the zero temperature limit. Plus, I introduce a new notation today, IT. This by definition is IMT minus I0. Minus I0. This is a zero temperature. Now we calculated this by identifying this as 1 over m del del m of the free energy at zero temperature, right? Because the reason that the I entered appeared in the analysis last time, okay, was because I is 1 over m del del m of the free energy of the field theory. Okay? That's the reason why we dealt with I in the first place, right? We calculated I and then we integrated this to get the free energy. So we calculated I naught as 1 over m del del m of, let me write it as F naught, but this is the free. There are two things. One is zero temperature, that's this zero over here, and the fact that I by them, the definition was 1 over m del del m of the free energy of the free theory, right? This free stands for the fact that it's a free energy of the free theory, right? Last time we didn't write it explicitly because we are dealing with free theory, right? We didn't have to write explicitly F free, but today because F refers to the interacting theory free energy, right? Whenever I am referring to free energy, free theory, I have to put a superscript or a subscript. Okay? That's what this is. More explicitly, this is 1 over m del del m of half integral d dk over 2 pi to the d of square root of k square plus m square. Right? Because you had seen that zero temperature free energy, right, is just half integral d dk over 2 pi to the d times ek, right? Ek is square root of k square plus m square. And I'll leave it as a simple exercise to check. Okay, of course it has to be the case that this is given by integral dk naught by 2 pi integral d dk over 2 pi to the d 1 over k naught square plus k square plus m square. Okay, all you have to do is that you start with this expression over here. Okay, k naught is running along the real axis. Then you close the contour, okay, either in the upper half plane or the lower half plane. Right? In that process, you pick up residues from k naught equal to either plus I square root of k square plus m square or minus I square root of k square plus m square. Okay. And by doing that, you will get an answer which involves only d dk over 1 over square root of k square plus m square, and that's exactly the mass derivative of this with respect to the mass. Okay. So it's easy to check that these two are the same. Okay. And the significance of this is that this is indeed the zero temperature limit of this. Right? If you take a t goes to 0 limit, this sum over n can be replaced by an integral, right? And that becomes dk0 over 2 pi, k0 square plus k square plus m square. Right? This is just a consistency check that even if you use this representation and calculate I0, it's exactly the same as what we calculated last time. Because last time we didn't calculate I0 explicitly, but we calculated by taking the derivative of the free energy with respect to the mass parameter. Okay, are there questions? Okay. Now, today of course we have got the result in terms of I, right? So why did we split it into I0 and IT? Okay, I could have just worked with I. The reason that we split it into I0 and IT is because if you recall the discussion last time, I0 had ultraviolet divergence. IT, which is, we calculated I independently, okay, which also had ultraviolet divergence, okay, and then we subtracted I0, okay, which was calculated from this formula over here, okay, and we found that while I have ultraviolet divergence, I0 have ultraviolet divergence, I minus I0 doesn't have ultraviolet divergence, right? Which was good because that when you integrate it back, you showed that the free energy of course has ultraviolet divergence, but that is only the zero temperature part, right? That overall constant, that is ultraviolet divergence, everything else is free from ultraviolet divergence. So the lesson that we want to recall from last time's discussion is that I0 is ultraviolet divergence, but IT is not. Is this clear? I0 is UV divergent, but T independent by construction, of course. This is zero temperature limit. I is UV finite and T independent.
IT.
Pardon?
IT.
I, thank you. I, okay, which is by definition I minus I. And let me recall also that F had the property that F free, I can write as F free naught plus F free. Okay, again let me write as F free T. This is a new notation. This is by definition F free minus F naught. The point is this is UV divergent. UV divergent. T independent. This one is UV finite. T independent. Okay, this is what we had found last time. Okay, in fact we calculated Ft by using the fact that 1 over m del del m of Ft is It. Right? We calculated It, which was UV finite, and then we integrated it to get Ft. So at the free level, things were nice because while we had UV divergence in the free energy, that UV divergence was just in the constant part. And the constant part we had said that you can just shift the energy, zero of the energy, right? And that will take away the constant part. Okay? A constant addition to the free energy, which is UV divergence, doesn't bother us too much. Okay? Because that's just can be removable by shifting the zero of the energy. But here we have a problem, because now you see that we have I empty whole square, right? lambda times I empty whole square, 8 times I empty square. If you write this as I naught plus IT, this becomes lambda over 8 times I naught square plus 2 I naught IT plus IT square. This is UV divergent because I naught is, okay, but this is temperature independent, so you don't worry too much. Right? This is again removable by adding a constant term to the energy. This is UV finite, temperature dependent, which is okay. But this cross term is problematic because I0 is UV divergent, right? IT causes the temperature dependence. So now in the expression for the free energy, we have a temperature dependent UV divergent term. Okay, that's not very physical, right? We don't expect temperature dependent UV divergent term. Okay, so something has gone wrong in this calculation. So what has gone wrong? Any suggestion what you should do? Why you are getting unphysical results like this?
So it should be I minus I0
I minus I0. So the calculation what we did are all correct, right? I mean, so what is problem? What is it wrong?
Free part also temperature dependent.
Pardon?
Free part has temperature.
Free part has temperature dependence, but that part is UV finite, right? So in the free part, the UV divergent piece is here, which is temperature independent.
So this squaring we got by just taking this.
Yeah, just diagram. This diagram. Any thoughts on this?
Because of the loop.
Yes.
Because of the loops.
Yes, of course the UV divergence is coming because of the loops. But how to get rid of them? How do you get rid of divergences from loops?
Lambda
Yes?
coupling.
Counter terms.
Yeah, you have to put counter term. What counter term?
The coupling lambda.
Yes. Coupling lambda.
Counter term for
Yeah, but if you take the counter term for lambda, that's itself of order lambda square, right? So that will not help to order lambda. Okay, what else will have counter terms? Yes? The mass. The mass is renormalized, right? Okay. So the M is a bare mass, right? So M is related to the renormalized mass. Okay, that M is renormalized mass plus something of order lambda. Okay. So if you put it here, it doesn't help, right? M is M renormalized plus order lambda, right? That again is of order lambda square. Okay, it will not help in cancelling order lambda correct, right? But this one, this depends on M, this also depends on M. Okay, so there if you write M as M renormalized plus a counter term, right? That's of order lambda. M is MR plus order lambda, right? Which is a counter term. That could give an order lambda divergent piece which is temperature dependent because Ft is temperature dependent, right? See, Ft was not UV divergent, right? As written, okay? But it has an implicit UV divergence because it's written in terms of M, right? So far we have only used, we have not done any normalization, right? Everything is written in terms of bare parameters in Lagrangian. Okay? So when you express M in terms of the renormalized mass, okay, can in principle give rise to a temperature dependent UV divergent piece. Okay. But of course then you have to check if it cancels that. Okay. But there is a possibility that once you renormalize, right, namely once you express M in terms of the renormalized mass, okay, then there can be a temperature dependent divergent piece. Is this clear? Okay. But the renormalized mass, right, the relationship between M and M renormalized, okay, that cannot be changed in a temperature dependent fashion, right? That is fixed once and for all by renormalization, right? That is, you have zero temperature. Okay. So it's not that you have a freedom of adjusting your relation between M and M renormalized to cancel off that term, right? Because that relation between M and M renormalized is fixed at zero temperature once and for all, right? And you have to use that. Is this point here? Right? Because you cannot renormalize dependent at every temperature, you cannot renormalize differently, right? That is the infinite part that you have removed, right? That's universal. Is this point clear?
So this FT free that you have written,
Yes.
this when written in terms of this bare parameter is not UV, we don't see this UV.
We don't see this UV divergence,
But
right?
if you write it in renormalized parameter, we will see that.
You could, because M and MR differ by order lambda, and that is epsilon dependent, right? That is UV divergence in principle.
Then we will have to make sure that when we write it, this IM in terms of this renormalized mass, then we don't get any.
Well, here of course, M and MR are the same, because difference between M and MR is of order lambda, right? So that will correct order lambda square, but not at order lambda. Okay? So the only possibility is from here. Okay, because this is zeroth order. Here when you write M in terms of MR, there is an order lambda term which could possibly give a divergent piece that can cancel this. Okay? So this is what you want to now see, okay? Whether this cancellation happens or not.
So then there will be such the temperature dependent but is common in both cases.
It should be, yes, right? That's what you have to check. That the temperature, well, it's not exactly common. We will see that it exactly cancels, but it happens in a somewhat non-trivial way. Okay, so let's do this. So let's go back to our TFT2 and renormalize. Okay, so renormalization means that M is just a parameter. Okay, you don't care if physical quantity is expressed in terms of M is divergent, but physical quantity expressed in terms of physical quantity should be finite. Right? That's the whole idea of renormalization. Okay? So you have to trade in M in favor of some physical quantity. Okay? And the physical quantity that we'll be choosing here is the physical mass of the scale. Okay? So instead of using, instead of expressing everything in terms of M, which is just a parameter in the original Lagrangian, we will now try to express everything in terms of the physical mass. Okay? So for this you have to find the relationship between M and the physical mass. Okay? So let's try to do that. So how do we calculate the physical mass? Okay? We have to calculate the physical mass to one loop order, right? Because we don't want to go beyond order lambda. Okay? And that is done by summing up all these diagrams and writing this as 1 over k square plus m square plus something delta, and then this we identify as the physical mass square, right? Because that's where the pole is. So our goal is to calculate this delta. For that, it's enough to just calculate this diagram, okay? Because this will just repeat itself here. Okay, so let's calculate this diagram. This is just 1 over k square plus m square, right? So let's write this. Here you have for the external propagators 1 over k square plus m square whole square. Okay. Then you have minus lambda over 4 factorial. Okay, that's for the vortex. Okay. Then combinatorial factor, right? What is the combinatorial factor here?
4 into 3.
4 into 3. Because the first line can go in any of the 4 legs coming out of this. This one can go into any of the 3 legs. Right? Then the rest have no choice. So 4 into 3. And then the integral. This is of course all done at 0 temperature, right? Mass renormalization is being done at 0 temperature. So this integral is dk0 by 2 pi dk over 2 pi to the d 1 over k square plus k0 square plus m square. You recognize this as something familiar? Yes? Yes? I0. Right? This is the 0 temperature limit of I. Right? This is I0. Sorry, this should be L. Okay, this I shouldn't confuse with this K. Let me call this P. Okay, external momentum. And this is K. Okay, so this is 1 over P square plus M square. Then 1 over P square plus M square whole square times minus lambda over 2 I0 plus 1 over P square plus M square cube minus lambda over 2 I0 square and so on. So this is 1 over P square plus M square plus lambda over 2 I0, okay, which is a function of M. So this tells us that the physical mass square is M square plus lambda over 2 I0 of M. Okay, plus order lambda square, of course, which we are always going to want to order lambda. We can also write this as M square as MP square minus lambda over 2 I0 of MP plus order lambda square. Okay, because inside I0 whether you write M or MP doesn't matter, the difference is of order lambda square. Okay, so I can just rewrite it this way. Is this clear? Okay, so now let's re-express this in terms of physical masses. So let me write F free as a function of M and T. Okay. And I am going to use this fact that M is related to MP by this formula. So what we are going to do is use the fact that the difference between M and MP is of order lambda. Okay. And you are only going to try to keep terms to order lambda. Okay. So we can Taylor series expand F free around the point MP, okay, and keep only up to the first order term in Taylor series expansion, right? Because that's order lambda, second order term will be order lambda square. The fact that it will also come with a divergent term square, that doesn't matter. In renormalization you always want to give an order, right? Second order you have to combine everything to see if the divergences cancel or not. So this is given by F free MP T and then let me write this as 1 over M del F free MP del M. Over 2M times plus order lambda square, which is here, plus lambda over 8 I mp square. Okay. So what I have done is that in the Taylor series expansion, instead of doing it in powers of m, I am doing it in powers of m square. Right? So 1 over 2m del f del m is like del m square of f. Right? So del m square of f times m square minus mp square. Okay? The higher order terms are negligible, and then you have this. So this is f free mpt 1 over m del f free del m. That is something else. Remember what it is? I. That I was defined that way, right? 1 over m del f del m was I, right? So this is half I mp times m square minus mp square, that's minus lambda by 2 I naught mp.
By MPT,
Pardon? Yes.
because M equal to
Yes, mp. At this level, it doesn't really matter whether it's m or mp because there's a lambda sitting here, right? But it's better to write it in terms of mp. Plus lambda over 8. Here also I'll write impt. Plus higher order terms, which you don't care. Is this clear so far? Okay, so now let's write this a little more. So this is f free mt, yes, sorry, mpt. Then we have minus lambda over 4. Let me write it I as I0 plus IT. Okay, so I0 plus IT times I0. The arguments are always NP and T. Okay, so I'm not writing anything. I0 of course doesn't depend on T. Yeah, I0 is that's I0. And then plus lambda over 8. This is I0 plus IT whole square. So that's I0 square plus 2I0 IT plus IT square. And now we see that the unwanted terms, right? This I0 IT was a problematic term, right? There is a T dependent divergent piece. This exactly cancels the IT I0 which comes here. Okay. So this then becomes f free mpt minus lambda over 4 I0 square. Let me write I0 is a function of mp only square plus lambda over 8 I0 of mp square plus lambda over 8 IT of mpt square. Okay. So let's try to reorganize this a little bit more. Okay. So let's write this as f free naught plus f free t as we are doing earlier. Okay, but everything now with the function of MP. So I can write this as F free naught, which is T independent of MP, and together this becomes minus lambda over 8 I0 of MP squared plus F free T of MP T minus lambda over plus lambda over 8 IT of MPT whole square. And now you see that there is neat separation between the UV divergent piece and the temperature dependent piece. This part is UV divergent, right? This was UV divergent. This also has UV divergence because I0 has UV divergence. But this is T independent. So this UV divergent piece can simply be removed by redefining your vacuum energy. Right? Just a constant shift in vacuum energy. Okay, this we don't care. This part is free from UV divergence. This is what I calculated last time. And so is this part. IT is just derivative of Ft, right, with respect to M, or 1 over MP del MP of this. So now we see that the temperature dependent part of the free energy is indeed UV, free from UV divergence. And this is a general result. To all orders in perturbation theory, one can show that as long as we use the renormalized parameters to give an order in perturbation theory and express the partition function or the free energy in terms of renormalized parameters, then there is no further ultraviolet divergence. So all the ultraviolet divergences that you may encounter in the finite temperature field theory are removed by the renormalization relations that we derived already in zero temperature field theory. So next time we will be considering the high temperature expansion or equivalent to the low mass expansion of this partition function. And we will see that because of the infrared problems, okay, which are new, which are not there in zero temperature field theory, the perturbation theory, okay, takes a somewhat different form in finite temperature field theory compared to zero temperature field theory. Okay, there is some additional resummation you have to do here which modifies the way the perturbation theory works in this case. Okay, other questions? Yes.
In calculating the green functions, etc., do not you have to kind of take into account that there is a background thermal distribution, either Bose-Einstein or Fermi distribution, and all the fields will kind of interact with?
Well, that is already included, right? If you calculate the Euclidean Green's function, right, then the fact that you have put the periodic boundary condition in the Euclidean time direction, right, that already includes all the effect of a thermal bath. Right? For example, the fact that you are dealing with bosons and not fermions, right, is already included because here the partition function that you get, for example, for this even at free field theory level, right, you automatically get the bosonic partition function. Right? You can see that you get the correct occupation number of particles with the Bose distribution. Right? So those are already included once you have used the field theory language. Right? Because field theory is automatically second quantized, right? So it already knows that about the Bose statistics. Okay? That the identical particles, when you count states, right, you have to count in a certain way. Right? Think of them as indistinguishable particles. That is already part of field theory. Right? And the fact that it's at finite temperature has gone in because we have started with trace with 3 minus beta h and derived the path integral.
So this whole result could be then can be written in terms of something multiplying the, say, the Bose distribution or the Fermi distribution.
Well, if you take just the standard Bose gas, right, you consider non-interacting Bose gas, right, or even if you introduce interactions, right, normally the kind of interactions you introduce conserve particle number, right, 2 bosons interact, go into 2 bosons. Okay. In field theory, on the other hand, you don't have particle number conservation, right. So 2 bosons can go into 6 bosons, right, in a scattering. Okay, all of these are allowed processes, right? In 5-4 theory, 2 bosons can go into 6 bosons. So a field theory, it's different from the what we will get in the standard Bose gas, right? In the interacting Bose gas, where you have particle number conservation.
In other words, you can't derive this free energy by integrating over some dispersion relation. That is, at the tree level, there was a sort of k squared plus m squared dispersion.
Exactly.
Which, when integrated over the Bose distribution, gives you the free energy.
Exactly. Yeah.
So this f that you have doesn't have an interpretation of the.
No, I think this doesn't have, because you are taking into account this particle production. Right? Yeah. So this is not given in terms of just a simple dispersion relation of non-interacting particles.
This IT will be activated at low temperature. This second term that you have.
Yes.
This IT MPT square, which is the new term coming from interactions.
Yeah.
Will it have a mass?
No, it will not have a low temperature, because at least at this level, right, we calculated IT earlier, it's exponentially suppressed at low temperature.
It is suppressed.
Yes, because it's the same IT that we calculated last time, right?
Okay.
Because this is given in terms of free theory,
Mm-hmm.
right? So yes, at low temperature this will not be activated.
It will not be activated.
It will not be activated. It's exponentially suppressed.
But the free theory was activated. I thought the free theory with the mass.
Well, it had an exponential suppression.
Oh no, in that sense that.
Oh yeah, that will be there. Yes.
Okay.
So at low temperature, right, this IT will get contribution,
Yes.
right? But it's like exponential of m over t square.
Right.
Right.
When the free theory had a T4 at high temperature,
Yes.
this looks like what? If you go to beta 0, the second.
The t goes to infinity
the
limit.
T infinity limit of this.
Well, this will be still t to the 4.
Okay.
Okay. But we'll see that when you try to naively go to higher orders, okay, if you are not careful, it will look like you are getting things like t to the 5 over n, okay, which is not sensible, right? And that's where the infrared divergence problem comes in, and you will see that when the problem comes because we have to actually resum. Okay. So you will get t to the 4 at high temperature, but the coefficient of the t to the 4 term, instead of having an expansion in powers of lambda, right, you will start getting terms like lambda to the 3/2. Okay, it will not be an integer part of lambda.
So when you talk of perturbation theory, are you also somehow expecting that the powers that you get,
Yes.
either exponential in something or beta to the power whatever or t to the power something, is preserved under perturbation? That is.
Well, we don't assume it from the beginning,
Yes.
right? We just use perturbation theory and see what we get, right? Because we are calculating perturbation theory in lambda,
Yes.
right? And naively what you would do is that you will calculate to given order in lambda, you will get these functions, and then you study its behavior at high and low temperature. Okay, that's what.
But it so happens in this case that it does give you t to the power 4 to any order in
Yes,
lambda.
it will give, if you are careful, if you do things correctly,
Yes.
it will give t to the 4. The coefficient is lambda dependent, and the lambda expansion of the coefficient is not in integer parts of lambda. Right? There are things like fractional parts, log of lambda, and so on. Okay, but indeed it has t to the 4. To any order, given order in perturbation theory in lambda, the t to the 4 behavior is intact.
And you also would not allow any thermal transitions in the theory. That is, there are no phase transitions as a function of temperature.
The point is, in perturbation theory, I think it's very hard to see phase transition. Right? So, if there is, it could happen that this perturbation expansion is not convergent. Right? Then there can be phase
If
transition.
I was coming down from high temperature, where of course there is no order,
Yeah.
supposedly, wouldn't I see singularities in the free energy or its derivatives at some temperature? I may not access the ordered phase as such, but the
If you
coming
knew
down
this as a
process-
function of lambda exactly, then of course you would see. Right? But because you are doing an expansion in powers of lambda,
Yeah.
right, I am not sure that it will be very easy to see if you only have terms up to a given order in lambda. Right? Typically, in the expansion in a given part in lambda, you don't see the phase transition. But it can certainly happen that if you are actually able to resum in lambda, right, then you may try to see some phase transition. Yeah, so my feeling is that in perturbation theory you will probably not see phase transition of any kind.
Even the series people do Partition summations to.
Yeah, so with those you may get something, right? If you can get sufficiently high order in lambda and do Partition summation, Yeah, then maybe you can try to use that to see if there is a phase transition. But if you just rely on perturbation expansion, right, I think then it's very hard to see where the phase transition will come from. Because you will really get t to the 4 times various parts of lambda. Other questions?
So here we can expand for 3 parts with n square because it is symmetric under n equal to minus 1, we can do this in part anything else.
Well, you can do it, I mean, as long as it has expansion, you can do it in terms of m, right? It's just a trick. I didn't want to do it in 2 steps, I did it in 1 step. Right? But if you expand in parts of m, right, we are expanding, see, if we have f of x, right, all you are saying that if we can, as long as you are not near x equal to 0, right, we are expanding around m equal to mp, as long as you are not near x equal to 0, right, whether you expand in parts of x minus x0 or x square minus x0 square, right, it doesn't matter, it's same expansion basically, right, you are expanding in a different variables.
But then we will not get the odd terms in this expansion, n cube and 2 by 5.
Oh, it's x square minus x0 square, right? See that problem that you are suggesting will happen if you expand around 0. If you expand around m equal to 0, then it's true, right? You will not get the odd term. But this is like expanding in parts of m square minus mp square instead of m minus mp, right? So there is no problem, right? You are right that if you are expanding around m equal to 0, right, then of course it makes a difference whether you are able to expand in parts of m or m square, right? There, unless you only have even terms, you cannot really expand in parts of m square. Right? Because otherwise, a term like m is like square root of m square, right? So this doesn't have a Taylor series expansion. But here you are expanding on m square equal to mp square, and that's why you are able to use m square as a variable. But if you are not comfortable with it, you can actually expand in parts of m also, right? It will give exactly the same result. I mean, you will not write it this way. You will write del f del m times m minus mp, right? Then del f del m you will write as m times I, right? Because 1 over m del f del m was I, right? So this will be m times I, and then this m minus mp you have to calculate. You calculate m square minus mp square, right? From that you can calculate m minus mp to first order n lambda, just taking the put a factor of half basically, right? And you will get exactly the same result. Any other question? Okay, so we'll continue tomorrow.